Yes. All right. Good afternoon. Welcome to this Frontier Symposium on cabin air environmental research. My name is Yan Chen. I'm from Tianjin University. So this is a national project sponsored by the Ministry of Science and Technology. First, I'd like to give a little bit of overview on this project. The research concerns the environmental control system, which means the air coming through the engine and compressed, becomes a high temperature, high pressure here. And then we have an air conditioning pack here, which will condition the air to suitable pressure and temperature, and then further send it into the cabin. And of course, to maintain the suitable, comfortable, and healthy conditions. And then a part of dirty air will be dumped through the outer valve to maintain the suitable pressure inside of a cabin. That's typically 0.8 ATM. And then another part of air, about 50%, going back through the filters and mixed with the fresh air. So why we want to do the research? Because according to a survey conducted by Park, which is actually from Airbus, showing that in most of cases, the cabin thermal comfort conditions are not very good. So people always feel too warm for the upper bodies and too cold for the lower bodies. That's the result shown here. On the other hand, the air quality could also be a problem. If you look at the trend of design in the past 50 years, the total fresh air coming to the cabin, or outdoor air coming to the cabin, decreased dramatically. And on the other hand, there's some problems related to the health. For example, the ozone level, because a lot of airplanes fly very high, where ozone level is very high. So this is a study conducted by Charlie Whistler, which showed that people might get a headache because of a high ozone level. And when the temperature is controlled at a different level, the perceived air quality is also different. And of course, you probably have seen these slides before. Infectious disease could be also a problem. And we also wanted to study how the air coming into the cabin. For example, by using this Boeing 787 as an example, now we do not get the air from the engine, but through a separate compression system, which will save the energy by 3%. And that's really a lot of money if you look at the entire airplane stock. And therefore, the Ministry of Science and Technology sponsored this project with US dollar 5.3 million, not $5.3. There's a 5-year project. And what we try to do is combine not only a single thermal comfort or air quality. So we try to do everything together. But when you do everything together, it's getting very complicated. For example, you might easily make the cabin comfortable, but the air quality might be bad. And therefore, it's a pretty challenging job. And what we try to do is look at the different problems. For example, when you combine different physical parameters, and then it's very difficult to do the measurement or the calculation because you need different equipment to do the same thing at the same time. And therefore, we try to understand what happens in the cabin. One major problem we try to solve is the unsteady airflow problems and heat transfer, unsteady airflow, heat transfer, and mass transfer problem. I will show you a little bit more. And another part is try to use inverse design theory to get the right air conditioning systems for this cabin. So that's the second part of the problem, how to couple and decouple different type of parameters in order to provide passenger and crew member the maximum comfort. So for the first part of the problems, in fact, we look at multiple scales from single person to the entire cabin. We also look at the jet flow thermal plumes, and this is a very complex procedure. For example, you can see here the scales. It varies from the full cabin is in terms of meters, tens of meters. If you look at the human lung, it's in terms of 10 to the millimeters. And therefore, we have very different scales. And how to solve multiple scale problems in one simulation is not that easy, and that's one of our major research. On the other hand, as you can see from these images, the airflow in the cabin are unsteady. Although the jet from the diffuser are steady, human beings produce the same amount of heat, but you look at the interaction is always unsteady. And it's a low Reynolds number, very difficult to predict and to measure as well. And therefore, we try to solve that. On the other hand, we also look at the cabin contaminants. You have the coughing, sneezing, breathing from passengers, which might contain infectious disease virus. And on the other hand, you also have the materials of the emissions from different cabin components, walls, seats, etc. So how they interact with the human being inside of a cabin at low pressure and low humidity. This is a very special condition for the cabins. Furthermore, we do not just do all the simulations. We have to validate our result, and therefore we use mock-up or even the whole plane to conduct the measurement of the air distribution, which include the air velocity, temperature, particle distributions, etc. So we try to understand the relationship between air distribution and the thermal comfort, age of air, the perceptions, etc. Furthermore, you saw this image before. We try to design the new air conditioning systems by inverse theory, which means we look at the thermal comfort, air quality, and energy efficiency as a design goal, and then try to understand the multiple factors together, and then in order to create a best cabin environment. So finally, we do this inverse simulation. I just quickly skip it. But finally, we want to look at the new type of air conditioning system, which later on Professor Zhang will introduce a little bit more. But currently, we are filing a patent on this one, so I'm not going to give a very detailed discussion, but we will try to do that a little bit later. So the total project is not only from the government. We also establish a consortium, so the industry also support us about $2 million. Then universities also have the funds for the equipment, etc. So the total project, in fact, is about $10 million. So we are doing fundamental applied research and proprietary research by 8 different universities. And today we are unable to report the research fundamentals because some other parties have some IP issues, so we cannot discuss that in detail. So we have a total of 6 thrusts, and we have different people on the podium today to report this. So first, if you want to know more about this, you can visit our website later to get this information, including all the publications available. So first, I would like to invite Professor Zhenxian Liu from Tianjin University to report on the first thrust, which is about numerical simulation of the air distribution. Professor Liu, please.
Good afternoon. My topic is numerical simulation strategy for unsteady airflow in cabins. The characteristics of airflow in cabin strongly coupled with the geometry and the flow parameters like the personalized vent, the main inlet and outlet, the passengers' heat loss, and etc. Also, maybe furthermore, in the future airline cabin, more requirement must be met, like the materials and need the panoramic sunroof and more comfortable space and more leisure feeling, and maybe a shopping like this. So it's really a challenge for the numerical simulation to obtain the detailed flow information, just using one appropriate the turbulence model. And so a numerical strategy is especially important. The complexity of the flow in cabin includes natural, forced, and mixed convection, and the flow shows the intermittent in space and in time, and also have multiscale vortex and complex boundary condition. So the problems need to be solved include 2 parts. One is the flow mechanism of thermal plume and the jet flow of personalized vent, and how these 2 types of the flow to couple with the main flow in cabin. And so we have to find appropriate models to get these details, the flow information, maybe RANS or LES and DNS. Another problem is how to carry out the computing tasks, and which maybe a large proportion of spatial scales and complex the boundary conditions. So we have to match in the mesh qualities and verify the mesh standard. Aimed at the above the problems, the numerical simulation will focus on the following aspects. The first one is the thermal plume, and what we try to get to is to identify the flow characteristics of the thermal plume with temperature difference. The second is the jet flow. The key work will focus on the flow field with the coarse mesh and appropriate the turbulence model. The third one is the main flow in cabins, and the last one is complex boundary conditions. And the analysis of the thermal plumes. Firstly, we calculated the the whole body with seated position to want to find the flow characteristics. And the total mesh is about 7.2 million. And the temperature condition is 32 and 30 and 24 separately. On the surface of the body, we arranged much mesh, and which the minimum the mesh size will satisfy the demands of the chronograph dissipation scales, which can be calculated using this formula. The top on the right, the graph shows the result of the velocity vectors, and it can be solved. The obvious, the unsteady vortex motion. And the bottom graph is the temperature contours distribution. In order to understand the detailed flow over the head, the unsteady vortex, we calculated in the area just overhead in the flow field. The total mesh about 4.5 million. And the top on the right is the temperature distribution. It's strange. The flow is steady, as is very different with the result from the whole body, the result. So next step, we calculated the bustle, the thermal plume, from the waist to the overhead, and with the mesh total is 9.7. The bottom, the two graphs shows the temperature contours, and it can be observed the obvious, the unsteady vortex, the motion, and the temperature boundary layers and generated from the body side and separated on the shoulder, and then to raise upward and producing the irregular vortex, the motion, and it's similar with the whole body. So we can obtain, for the head, we can find the fluctuating of the velocity and the temperature. It means it's a stable plume. But for the bustle, it's half body. We can see an obvious separation of the boundary layer on the shoulder, leading to regular vortex shedding. The frequency is less than 1 Hertz, producing obvious unsteady vortex overhead. Is similar with the seated position, the whole body, this result. The middle two graphs is at the same position marked by the red line, is respectively of the half body and the whole body, the velocity distribution. It indicates have a similar velocity distribution. And the top on the right is temperature boundary layer, is same with the velocity boundary layer. Its thickness is about 2 centimeters. And the middle two graphs is instantaneous velocity data at the 2 points marked by the red dot was transferred to the spatial frequency information by using Fourier transform. It can be seen the large power happens at the low frequency, less than 1 Hertz. It means the fluctuation within 1 second is not obvious. The table below is the heat flow rate per unit area and the total dissipation rate converted to the whole body. The magnitude is correct according to the experiment date. Analysis of the jet flow. The top the top left is the flow field, and the middle one is a comparison of numerical simulation and the experiment date. And the top on the right graphs is a non-dimensional velocity distribution. It can be seen all the velocity is coincidence. So it can be represented by a fitting function. On the bottom left is 3 types of the velocity profiles was given to test the influence of the inlet velocity profiles. The bottom 2 graphs shows the result. The left one is within 8 times diameter. It can be seen at the cone area is different, but the far flow away is the same. And from the 8 times diameter and further on, all the velocity distribution is the same. It means the flow field hardly affected by the inlet velocity profiles. Also, the different mesh number be compared from the 5,000 to 0.8 million. The top on the left shows it must be greater than 116,000 mesh number. We can't correct the flow characteristics, but this mesh number is too much for couple with the airflow in cabin. So considering the dissipation generation and the dissipation terms in epsilon equation, the factors C1 epsilon and C2 epsilon corrected by the mesh size and the Reynolds number means we can't get modified the factors. These 2 graphs shows the result of comparison. The green line is the after. We use the modified the turbulence model, and the red one is not before modified, and the black one is 0.56 milli mesh. It can be observed. The result, the green one with 5,000 mesh number is same with that of the 1.56 milli mesh. It means the modified turbulence model, it can be used in coarse mesh and get the correct flow field. We also applied the turbulence, modified the turbulence model to different flow with Reynolds number from the 500 to 2,000. It's very good. So next step, we plan to use the modified the turbulence model to coupling with the cabin and decreasing the mesh number and to achieve the processing simulation fastly. The analysis of the main flow in cabin, the single row, the mesh is 5 million about. We calculated the flow field with RANS and LES without thermal plume and jet flow. The left graph shows the result of RANS. It can be seen is a steady flow field, not the unsteady, and that is a symmetry. LES shows the obvious the unsteady the flow with tinier velocity and greater relative fluctuation. The unsteady characteristic frequency is less than 1 Hz. It's the same with the whole body the result. We also calculated the Grashof numbers and the Archimedes number, and to investigate the ratio buoyancy and the viscous force. The bottom of the graphs, it indicates the buoyancy lies in the amongst of the body and close to the windows. Also shows with the Archimedes model, top on the left. Bottom on the right shows the construction of the vortex core and the streamlines, shows a complex 3D construction. So from the above the research, we can conclusion the following from the 3 parts: the thermal plume, personalized ventilation for jet flow, and the airline cabin, the main flow characteristics is the same above just we discussed. As a result, the following simulation strategy can be applied to the simulation of in-cabin. That's for the jet flow of personal vent, we will use the coarse mesh and the modified turbulence model to get the corrected flow characteristics. And for the passengers' heat loss, we will arrange the developed velocity boundary layers on the bottom of the body side, and to generate the separation on the shoulder in the coarse mesh. And in the whole cabin, the flow field will be using the coarse mesh with the modified turbulence model, will be a total mesh will be controlled less than 0.5 million mesh number. Our target is correct fast acquisition of flow field information with thermal plume, complex boundary conditions, and the geometry in airline cabin. Thank you.
Thank you very much. Our next presenter is Professor Ginger Liu from Tianjin University, who will talk about the measurements.
Okay, so my presentation is about evaluate for the air quality and thermal comfort in airliner cabins. Actually, the number one task is a simulation method to predict the air distribution in cabin. My target is for the validation of safety models and also display and investigate the design concept of the cabin ventilation systems. And in our project, I have 3 detailed targets. One is we make detailed and accurate experimental mesh in mock-up and also in full size of the aircraft cabins to validate different simulation methods. And also we use the different experimental data to have the air velocity and the temperature and the contamination field data. These 2 data will be the benchmark for the future design of the cabin. And also we will check the turbulence characters for the deep understanding of the airflow characters in the cabins. Here is the preliminary result. So far, we already built up 4 kinds of cabins. One is use as a real aircraft. We bought a retired MD-82 aircraft from China Southern Airlines. So this aircraft, we use the insulation materials to make the interface temperature now variate according to the outside temperature variation. And also we design mock-up. This mock-up has 7 rows, and also parts of the mock-up is transparent. It can be used for the PIV measurement. And we have the simple mock-up to make the jet and the supply outlet test. And also the fourth one is we have the mock-up to test the thermal comfort with gas flow and with the normal general supply systems. Here is our PIV system used for the 7-row mock-up. We put the high power laser. Okay. So we use the high power laser to put the light into the section of the cabin, and we use the very high resolution CCD camera to get the air velocity. We use the ultrasonic anemometer to get the detailed air velocity in the MD-82 aircraft, and also we get the tracer gas system to measure the contaminant concentrations. For the real aircraft, you can see in order to reduce the error of the location difference, we use the automatic robot system to control the location. Here is some data we got it from the PIV measurement systems. Our PIV measurement, we can get the 1 meter by 1 meter, 1 meter by 1 meter resolution. It means we can get very detailed air velocity in the whole airfield. In the whole airfield, we use several different pictures to put together to get the whole picture. Example for the section. We get 1, 2, 3, 4, 5 pictures. One picture, the size of the pictures is about 1 meter by 0.6 meters. We put the different pictures together and get the average whole air velocity field. This air velocity showed in the picture is only 7 vectors plotted because it's too much. And also we average 100 samples for the PIV images to get the air velocity field. Here is some transparent data to show that from the picture you can see in different pictures you cannot take the picture at the same times. But when you make the time average, you can get the whole trend air velocity very well. For the temperature and for the thermal boundary condition of the supply outlet, we use the UV ultrasonic anemometer to get the direction of the air velocity from the outlets, and also we use the full anemometers to get the detailed air velocity